Welcome to the video lecture on solving exponential and logarithmic equations. The first kinds of problems that we're going to solve today are exponential equations, and there's two different major strategies that you're going to use. The first couple of problems that we're going to look at are kinds of problems where it's possible to make the bases on both sides be the same number. If that's doable, then you're going to make the two bases be the same and then just equate the two powers. So for example, if I have 3 to the x equals 9 to the 5x minus 3, how can I make those bases be the same? Well, we can't make the base 3 get any smaller, but I know that 9 is a perfect square, it's 3 squared. So if I change this 9 to 3 squared, all of that is being raised to this power 5x minus 3. I'm not doing anything to the left side. And on the right side, we have a power to a power, so the law of exponents that applies here is to multiply. And when you multiply here, we do need to distribute. So it's going to be 2 times 5x and 2 times 6. So the right-hand side would become 3 raised to the 10x minus 6. Now this is good because now that the bases are the same, the only way the bases can be equal and have the equation be true is if the powers are the same. So we're going to set the two powers equal to each other, and this is just a nice linear equation, so I can subtract 10x to the other side to isolate my x's, and then just divide through by -9. And reducing, we can divide the top and the bottom by -3's, so this would become 2/3. So one type of exponential equation that you'll see is when it's possible to manipulate the bases and make them be the same. And if you can do that, then you're just going to set the two powers equal to each other and solve. Let's try another example like that. So if we look at this next one, it looks pretty intimidating, but if you look at this 1/8 and this 4, those are your bases so far, and right now they're not equal, but you should recognize that 4 can be rewritten as a power of 2, 2 squared, and 8 can be rewritten as a power of 2, it's 2 cubed. So how do we rewrite 1/8? Well, if 8 is 2 cubed, and we want that 2, that base of 2, moved up to the top, what's going to flip this up? That's what negative exponents do. So this would become 2 to the -3 power. So 2 to the -3 is the same as 1/8. So let's substitute in 2 to the -3 for the base on the left side, and let's substitute in for this 4 a 2 squared. So now we've forced the two bases on the left and the right to be the same, base 2. Now let's simplify. We have a power to a power, so we're going to multiply, and we get 2 to the -3x squared. And on the right side, we also have a power to a power, but we do need to distribute. So this is going to become 2 to the 8x minus 2 times 3 halves. The 2's are going to cancel, just giving you that 3. Now we need to set the two powers equal to each other since the bases are equal. So this is going to be -3x squared equals 8x minus 3. Now this is a quadratic equation, so we have a slightly different strategy to solve this. We want to get a 0, so I'm going to go ahead and add 3x squared to the right side so that it becomes positive. And writing this in descending order, I get 3x squared plus 8x minus 3. Now if we're lucky, this is going to factor, so let's see if we can get it to factor. Two sets of parentheses. If I put a 3x and an x here, and I put a 3 and a 1 here, that'll give me 9 and 1, and that will give me an 8. I want a positive 8, so I'm going to need to make this positive 9 and minus 1, and that will also give me this minus 3 on the end, which I want. So this works, and that means my two solutions are going to be 1/3 for the first factor and -3 for the second factor. Okay, so again, setting the two bases to be the same base. If that's doable, go ahead and change your bases so they match, and then you can just set your two powers equal to each other and solve from there. So that's one kind of exponential equation that you'll be asked to do. The other possible strategy that you might need is if it's impossible to get the bases to be the same. So that's this step 2 here. If it's not possible to get the bases to be the same, we're going to isolate the variable term and we're going to take the log of each side, because if we're trying to undo an exponential to get at its power, the inverse of an exponential is a log. So that's why we're going to use a log of both sides. And then we may need to use some properties of logs to rewrite it a little bit, and then we're going to solve from there. So let's try a few of these examples. So for example, 2 to the 3x equals to 34. The reason I can't make these bases be the same is because 2 is already as low of a base as I can get, and 34 cannot be rewritten as 2 raised to a power. So that means we're going to have to resort to logarithms. If we want to get at that x that's up here in the power, the only way to undo the base is with a log. Now when you're doing logarithms, usually, since we sometimes want to know decimal values for our answers, usually we're going to want to stick with using either a log base 10 or a log base e, which is an ln. And the reason you want to use those two bases is because those are usually the keys that you have on your scientific calculator. So I am going to be taking a log of both sides, and it can either be a common log, base 10, or an ln, and it doesn't matter which one you use usually. So on this one, let's just take an ln of both sides. So it's going to look like this. Ln of the left side equals ln of the right side. Now, by doing the ln of both sides, you're maintaining the equivalency of the equation, so we're not changing or losing any of our solutions. Now, here is where those properties of logarithms come in handy. We want to get at this x, which is up in this power, and we have a property of logarithms that says if you have ln of something raised to a power, you're allowed to bring that power down out front. So that's what we're going to do. It gets brought down out front and gets multiplied in front of that ln of 2. So the whole reason why we're taking the ln of both sides is so we can use that property of logs to bring that power down to this level, which is the level that we want it at, so we can solve for it. At this point, we just want to isolate that x and get it by itself. Both the 3 and the ln of 2 are being multiplied by the x, so to undo that, I'm going to divide by both the 3 and the ln of 2. So x becomes ln of 34 divided by 3 ln of 2. Now there's multiple ways to change this answer. I'm just going to leave it like this. If you wanted to know the calculator value, the decimal value, then you would just hit ln of 34 divided by, make sure you use parentheses because we want to divide this ln of 34 by both the 3 and the ln of 2. And our decimal is 1.6958. So it's approximately that. That would be your approximate solution. This would be your exact solution. So make sure you're able to do it both ways. So let's try this again on the next example. We're not able to make 10 and 6 match. We're not able to make these two bases be the same. So that's where you have to break out your logarithms. And in this case, there might be a slightly better choice for what we choose to use for our log. Remember I said you could either use log base 10 or log base e. And since I see a base of 10 over here, I tend to try and use log base 10 if I have a base of 10 so I can get some cancellation going on. So you can still use ln's on this problem, but let me show you why using a log base 10 might be a little more clever. So I'm going to take the log of both sides, and remember when you don't write the base in there and you just see log, that's implied to be a base 10. So there's implied to be a base 10 down there. Now the reason why this is nice is because we have a cancellation property that says if you have log base a of a raised to a power, the log base a of the a cancels out, giving you just that power back again. So these are going to cancel out since the base of the log is the same as the base of the exponential, and we will just get a 1 minus x on the left side. So that log totally disappears, which is the good news. Now on the right side that doesn't happen because this is base 10 and over here we have a base 6. So we're not going to get that cancellation. However, we can still manipulate this and use that property of logs, which says that we can bring the x out front and multiply it by our log of 6. Now this time we have two x terms, so I do want to get those together on the same side of the equation. This is considered a linear equation because they're both x's to the first power. So I want to get my x's together, so I'm going to add x to both sides. And because there's two x terms over here, the way to go from this point on in the equation is to think about factoring out that x like a GCF. These two terms, separated by that plus sign, have an x in common. So if I factor out x, I would be left with log of 6 plus 1. And then, to isolate the x, I can undo this multiplication by dividing by this entire quantity. So x is equal to 1 divided by log of 6 plus 1. And that's your exact solution. If you wanted to get the calculator value, then you would just do 1 divided by, and you need parentheses, log base 10 of 6 plus 1. And we get 0.5624 if I round off. Okay? Alright, let's try the next one. Again, we have two bases, a base e on the left and a base 6 on the right, and it's not possible to make those two bases match. So here we're going to need to use those logarithms so that we can get at this x up in the power. And using the right base on our log is essential here, is key to making our lives a lot easier. Because I see a base of e, then we're going to want to use a log base e as well, which is called an ln, a natural logarithm. So let's take the ln of the left side and set it equal to the ln of the right side. Now just like in the last example, since this ln is a base e and our exponential is a base e, these are going to cancel each other out, just giving me that power by itself. We don't have any x's on the right side. This is just a constant decimal over here. So the only x is over here. So let's isolate it by adding 1 to both sides. And then I want to divide everything through by 3. And then I need to undo that square, so I'm going to take a square root of both sides. Remember that when you take a square root of both sides, you get a plus or minus solution. So we are going to get two answers here, plus or minus square root of ln of 6 plus 1 all over 3. You can get fancy here and rationalize your denominator and do all that kind of stuff. Me personally, as an instructor, I don't mind just leaving it like this. I don't find the need to try and make it look nicer or look too fancy. Usually in this case you probably just want to know what the decimal is anyway. So I'm going to go ahead and find the decimal. We want the square root of parentheses ln of 6, whoops, too many keystrokes there. Square root of parentheses ln of 6 plus 1, close the parentheses, and I want all of that divided by 3, close the parentheses for the square root, and we get 0.9647, and it's plus or minus in front of that. So these are my two solutions, exact and approximate. Okay, the next example here is a little bit different because we don't have that exponential isolated. The power, or the exponential part that I see, is this e to the negative x, and right now it's part of this denominator. It's not by itself on one side of the equation. So we're going to need to do a little bit of work first to try and isolate this exponential, try to get it by itself on one side of the equation before you start taking ln's of both sides. Otherwise it's just going to get way too messy. So how can we possibly get rid of this denominator? Well, just multiply through. We have an equation, so as long as you do the same thing to both sides, if I multiply both sides by this denominator, that should clear it out on the left-hand side, giving me just an 8. And if I distribute my 5 across, I'll have 5 plus 5e to the negative x. So now I have that e to the negative x on this level, which is good, but it's not isolated. So the next thing I'm going to want to do is try to get rid of these 5's. First, I have to get rid of this 5 that's further away by subtracting. And then this other 5 I can get rid of by dividing. So I get 3/5 equals e to the negative x. And now that exponential piece is isolated. There's no coefficients in front of it. There's nothing added or subtracted off to the side. You want to get to this stage first before you start taking your ln's. And I want to use an ln because I have a base of e. So it's going to give me a lot simpler answer using an ln. So I'm going to take the ln of the left side and the ln of the right side. Because ln is base e, the ln of the e cancels out, giving me just the minus x. And finally, to finish solving for x, I could divide through by this negative, which is just going to make it become a coefficient out front of that ln. Now, chances are, if you're looking in a textbook, it's not going to list this as the answer, because it's not as cleaned up as it probably could be. One thing that you often see done here, especially with these negatives, is you can take that -1 and think of it as an exponent. And what does a -1 exponent do to a fraction? It flips it over. So this is the same as the ln of 5/3. So this is a little bit cleaner looking than negative ln of 3/5. You don't have to do that, but it is an option. And then in terms of the decimal, we're going to get 0.5108. So this is approximately 0.5108. Okay, the next two examples are also exponential equations, but they're a little bit different. A couple things that you should notice here is that you see more than one exponential expression. We have a 3 to the 2x and a 3 to the x. So that's going to make this a little bit tougher to deal with, plus the powers are different as well. One thing that you might want to notice here is if you subtract that 2 over to the left side and get a 0, this does have potential for factoring. And if you're confused about that, sometimes what you'll see done, and this is just an option, but sometimes what you might see done is a change of variable. Let's let m be the expression 3 to the x. Then what would 3 to the 2x be? Well, that's 3 to the x squared. So that's the same as m squared. And the reason again is because that's like 3 to the x, which is our m, quantity squared. So in other words, this expression or this equation that I have right here could be rewritten as an m squared plus an m minus a 2. This is called doing a change of variable. You don't have to do that, but if you do that, it might help you see a little bit more clearly why this will factor. If you set up your two sets of parentheses, we have an m and an m to get our m squared. We would need a 2 and a 1 to get our 2, and I'd want the 2 to be plus and the 1 to be minus. And then that would give you m equals to 2, and m equals to negative 2, and m equals to positive 1. Now that's not your final solution because that's what m is, that's not what x is. So we would have to then substitute back in what m was equal to in terms of x. So m was 3 to the x, and we want that to equal negative 2. And over here, for this equation, we would want 3 to the x to equal 1. And so then we would have to solve each of these. So let's go ahead and do that. If I take a look at this left one over here, in order to get at that x, I would need to take an ln of both sides, or a log base 10 of both sides, because there's no way I can get these bases to match. So the ln of 3 to the x has to equal the ln of negative 2. Now right here is where you should stop, because you know that you can't take the ln of a negative number. Logs of 0 and logs of negatives, no matter what the base is, do not exist. You could have seen that from up here as well, because 3 to the x never equals a negative number. In fact, it has that horizontal asymptote at 0, which means 3 to the x never crosses the x-axis. So this is impossible, which means this part of the equation isn't going to contribute any solutions. So there's no solutions from this part. However, we might have a solution over here. So let's take the ln of both sides for this second equation. So ln of 3 to the x equals ln of 1. What is the ln of 1? If you take base e, what power would you have to raise base e to get it to turn into a 1? You would have to have a power of 0. So the ln of 1 is just 0. On the left side, using those properties of logs, I can bring this x down, and to finish solving for x, I can divide both sides by that ln of 3. And 0 divided by ln of 3 is just 0. So my only solution is x equals to 0. Now up here I did this with a change of variable. You could have avoided that just to show you what that would look like. You could have factored directly from here if you see that that's possible. And one thing to look for to know that factoring is possible is when the power on your middle term is exactly half the power on your leading term. And if you have something that is in sort of that trinomial format where the power of the middle is half the power of the leading term, usually those are the kinds of problems that are going to factor. So this would factor into 3 to the x times 3 to the x. When you multiply those bases, you add their powers, which is why we would get back 3 to the 2x over here. And then I would need a 2 and a 1 to get that minus 2. I'm going to need a plus and a minus. And that would give me a 2 3 to the x and a minus 3 to the x, which gives me a plus 3 to the x in the middle. So you could have factored it directly into this stage. That's fine. If that confuses you, then use a change of variable and rewrite it in terms of some new variable so it looks more familiar. But when it's all said and done, the only solution we're going to get for x is 0. Let's try that again on this example. So what you want to see on this one is, again, it has two different exponential expressions with two different powers. We've got an e to the positive x and an e to the negative x. So it's a little bit confusing about where to start, because normally when we're trying to solve exponential equations, we try to isolate the exponential and get all the other stuff on the other side. We can't do that here because we have two different exponentials and we can't get them sort of separated from each other. So what we're going to do is work with the only one that we know how to manipulate, and that's this one right here with the negative exponent. What does a negative exponent do to an expression? It flips it over and makes it a reciprocal. So the only place to kind of really start here is to rewrite this by flipping over that e to the x down into the denominator. And then we have a fraction, which you might think that makes it more difficult, but it actually gives us another place to go. It gives us another path to follow along in terms of solving this equation. How do I clear out denominators? I multiply by what the denominator is. So I'm going to multiply the left side by that e to the x and also the right side. Now what do you get when you multiply an e to the x times an e to the x? Remember that you add powers. So the base is going to stay e, and x plus x makes this a 2x. When I multiply e to the x times the fraction, the e to the x's should cancel, giving me just that 12. And then on the right side, 1 times e to the x stays e to the x. Now what I'm going to do is make this look very similar to the last example. I'm going to subtract that e to the x and sort of squeeze it in between these two terms, get a 0 on the right side, and put this in descending order. So this is e to the 2x minus an e to the x minus a 12. And what should sort of strike you as being similar to the last one is that this is a trinomial. It has 3 terms, and the power on the middle term is half the leading power term. So that means this probably will factor. So instead of doing a change of variables on this one, I'm just going to go ahead and factor it directly. But you could let, if you wanted to, you could let m equal e to the x, and then this would become an m squared minus an m minus a 12. That's another way to do this problem. If you wanted to do it directly, you would know that you would need an e to the x times an e to the x to get back that e to the 2x. You also need that e to the x to give you that correct middle term. And I would need a 4 and a 3 to get 12. And if I want a minus 1 in the middle, then the 4 needs to be negative and the 3 needs to be plus. So each factor then gets set to 0. This gives me e to the x equals to 4, and this would give me e to the x equals negative 3. So when I go to try and solve this for x, because we're not done yet, we don't have this as x equals, we have it as e to the x equals. So in order to solve it for x, I can't get my bases to match, so I'm going to have to take an ln of both sides. So ln of e to the x equals ln of 4. ln is a base e, our e to the x is a base e, so these should cancel, giving me x equals ln of 4 as one solution. Now when I go over here, hopefully you can see right away that this doesn't exist, because just like in our argument over here where there was no solution, the same argument applies. I'll draw you a graph here to visualize. E to the x is exponential growth like this, and it never crosses that x-axis. So there's no way that this graph is ever going to equal negative 3 way down here. So it's not possible for an exponential to take on a negative value. So this has no solution, so the only answer is our ln of 4. Okay, so these were all of our problems on solving exponential equations. What we're going to move into next is solving logarithmic equations. So the strategy for solving logarithmic equations is to try to get the logarithm isolated on one side, just like what we do when we're trying to isolate our exponentials. We're going to do that as well for our logs. So get the log by itself, and then what you're going to want to do is undo that log by rewriting it in exponential form, which is kind of the same thing as taking the exponential of both sides. And then once you've undone that log by rewriting it as an exponential, then you should be able to solve from there. The one thing that you really want to make sure of, and this is only important when you're talking about log equations, not necessarily for exponential equations, is you have to worry about the domain. Because remember that the domain of a log is that you can only take the log of positive values. So everything between 0 and infinity, not including 0. So you have to make sure that whatever your x value is for your solution, if you plug it back in, you never want to be taking the log of something negative or the log of 0, because that would be undefined. So we are going to have to always make sure that we check our solutions for log equations. So let's start off with a fairly basic one here, because it's already got our log base 4 isolated. It's log base 4 of some stuff equals to 2. There's no coefficients in front of the log. There's nothing being added or subtracted off to the side. So it's isolated, which means we can jump right in and undo this logarithm by rewriting it in its exponential form. So remember, this log equation means the same thing as base 4 raised to the second power has to equal this argument, 3x minus 2. So now there's no log left over at all. We've rewritten this completely. 4 squared is 16. And now we just have a nice linear equation. So I'm going to add 2 and get 18. And then I'm going to divide by 3 and get 6. Now you want to check. And really the only thing you're worried about when you're checking is the domain issue. So if you were to take 6 and plug it back in for that x, you just want to be making sure that whatever you end up with right here in these parentheses for that log, it needs to be something positive. So if I plug in 6, 3 times 6 is 18, 18 minus 2 is 16, and that is positive, so that's good news. That means our value of 6 is valid. It's not going to violate our domain. Okay? Alright, let's try another one. Here again, we have a single log. It's isolated. There's no coefficient in front. There's nothing added or subtracted on the side. So we're ready to undo the log right away by rewriting this as an exponential. You take the base of your log, raise it to this number on the right-hand side, so 5 raised to the second, and that has to equal all of this stuff, all of this argument. 5 squared is 25. And this time what we're left with is not a linear equation, it's quadratic. So I'm going to get a 0, and we have x squared plus x minus 21. The only good factors of 21 would be 1 and 21 or 3 and 7, and neither of those are going to give me a 1 in the middle. So it looks like we're going to have to break out the quadratic formula on this because it's not going to factor. So that means x equals minus b, which is 1, plus or minus b squared, 1 squared is 1, minus 4 times a times c, all over 2 times a, 2 times 1. So this is going to give me, on the bottom, just a 2, and under that radical, minus times minus becomes plus, so this is 1 plus 21 times 4, so I get an 85 under that radical. Now let's get a couple of decimals here. So I am going to need parentheses for that numerator, a negative 1 plus square root of 85, close the parentheses, and I want to divide all of that numerator by 2. So the plus case is going to give me 4.1098. And then if I do second enter, that just re-types back in the command I just used. And I'm just going to back up too far and change that plus. Sorry, my pen again is being frustrating. And just back up and change that plus to the minus case. And the other decimal that we get is negative 5.1098. So before we circle both of those, you have to consider that domain issue. So you're going to have to take each one of those and plug them back in. Especially important is this quantity right here. You want to make sure that whatever you get here is something positive. Now hopefully you can just see that if I were to plug in a positive x, square it, and add it back in plus 4, that's going to stay positive. So definitely the plus case is fine. If I take a look at the minus case, I'm going to get approximately negative 5. When I square that, that's going to become positive 25. Minus 5 plus 4, that's going to stay positive as well. You can verify that on your calculator if you want to be more specific. But both of these do work because when I plug them back in, I end up taking the log of a positive number. And that's all that we're worried about, is making sure that we're staying within that domain of all positives. Okay, let's take a look at the next example. This one is very basic looking. It's just ln of x equals to 8. The only thing you need to recognize here is since this ln is already isolated, we're ready to undo it by rewriting this in exponential form. So you have to remember that an ln means base e. So to undo this, we would just take that base e, raise it to the 8, and that has to equal to x. And there's our answer. Okay? And you can get a decimal for that if you want. So that would be 2,980.96. Okay? All right, now let's take a look at the next example. What makes this one different from the last three is this time I see two different logs. So what we need to do is be a little careful here. In order to undo our logs, we need to be able to rewrite them in exponential form, but I can't do that unless I have the log isolated by itself on one side of the equation. So what we need to do is consolidate these two and make them into a single log. We can't deal with two. We need to make it into one. And luckily we have properties of logs to help us do that. So if you have the log, remember, if you have the log of A plus the log of B, as long as the bases on those logs match, a sum of two logs becomes the product of their stuff, the product of their arguments. So that's what I'm going to apply right here. This could be rewritten, consolidated, as a single log base 4 of the x times the quantity x minus 3. And if you want to go ahead and distribute that x across, this would become x squared minus 3x. Now we have it as a single log. There's no coefficient, there's no numbers off to the side, so it's all nice and isolated. So we're ready to just rewrite it as an exponential. So this becomes 4 to the first equals x squared minus 3x. 4 to the first is just 4. And we have a quadratic equation, so I'm going to get everything on one side by subtracting that 4 and getting a 0. And this looks like it's going to factor. If I set up my two sets of parentheses, x and x, 4 and 1, I need the 4 to be minus and the 1 to be plus. So I get positive 4 and negative 1. And now you need to check your answers. So if I take 4 and plug it back in, here I would be taking the log of a positive 4, which is good. And if I plug in 4 up here, 4 minus 3 is 1, which is positive as well. So 4 works. If I take negative 1, that's bad news, because then we're trying to take the log of negative 1, and we can't take the log of any negative number, no matter what the base is. So this violates our domain issue, so it's not a solution. So only 4 works. Okay, we're going to do something similar on this next one, except this time we have 3 different logs going on, and we have one log that has a coefficient on it as well. So there's a couple things that we can do here. On the right hand side, we can do exactly what we did in the last problem and consolidate these two logs together by using that multiplication rule. So the sum of these two logs becomes the single log of the product of their stuff. So the 2 times the 3x minus 4. On the left side, we're going to want to get rid of that coefficient 2, and the way we can do that is by bringing it back up to our power, and that was our power property for logs. So this could be rewritten as a log of x squared. Okay? Now notice something on this one. If you have two logs equal to each other, there's a couple different ways that you could kind of progress at this point. You could notice that if you have log, and in this case it's base 10, log base 10 of x squared equal to log base 10 of this quantity here, the bases on the logs match. So the only way log of stuff equals log of stuff is if the two stuffs equal to each other. So you could note here that this forces the x squared to equal the 3x minus 4. It's kind of like we're undoing the log on both sides. The only way the log of A can equal the log of B is if A equals to B. That's really what we're doing here. So the only way log of A can equal log of B is if A happens to equal to B. So let's go ahead and solve this now. If I distribute my 2 across, we get a quadratic equation. Move everything to the left side, get a 0, and let's try to factor. We need an x and an x, and 8 I can do with a 4 and a 2. If I make them both negative, that'll give me a negative 6 in the middle. So this is going to give me x equals 4 and x equals 2. And then we want to check our solutions. So if I take 4 and plug it in here, I'm going to be taking the log of a positive 4, so that's good. We want log of a positive. And if I take 4 and put it in here, 3 times 4 is 12, 12 minus 4 is 8, which is also positive. So this one works. If we try 2, log of 2 is good. 3 times 2 is 6, 6 minus 4 is positive 2, so that works also. Okay? All right, next example. Here we have two logs with different bases, and they're what we call nested inside of each other. So we're taking the log base 4 of the log base 2 of x minus 1 equals to 0. So you want to kind of think of this as like an onion. We want to unpeel the layers or unpeel the logs and slowly work our way to the inside to get at that x that's way on the inside of all these parentheses. So the outermost log here is this log base 4. So to undo that, we're going to rewrite it as an exponential. So 4 raised to the 0 has to equal its stuff, and its stuff is all of this inside the parentheses. Now simplify. What is 4 to the 0? That's just a 1. So now we have this down, instead of having two logs, now we only have one log, but we still need to get at this x, so we still need to undo this log base 2. So to undo that log base 2, we're going to rewrite it as an exponential. 2 to the first has to equal this stuff right here, x minus 1. 2 to the first is 2, and if I add 1 to the other side, that's going to give me x equals 3. And if we double check into our domain here, 3 minus 1 is positive 2, which is good. So 3 is our solution. Okay, now we're going to look at some more miscellaneous types of problems. This next one is kind of a mixture of both an exponential and a logarithmic equation. So it's exponential because this is 3 raised to stuff, where there's a variable involved in that stuff, and then it's also got a log in there as well. So when you look at this, what needs to strike you is the fact that you have an exponential on the left side that's a base 3, 3 raised to a power, and on the right side you have a 27, which can also be thought of as a base 3. So this is one of those exponential problems where it's possible to make the bases match. So you want to do that. If you didn't do that, you could still make this work, but it's going to get pretty messy when you start using all these various logs. So it's much more direct, much more efficient to change that 27 to a 3 cubed. And now the only way this equation can be true if the bases already match is if the powers are equal. So we can lose those base 3's and just set the powers equal to each other, and now we need to solve this equation. Now this equation has a fraction in it, so we're going to want to undo or get rid of the denominators by multiplying both sides by the denominator. So I'm going to multiply both sides by a log base 8 of x. That's just going to cancel out that denominator on the left side, giving me 2, and the right side will be 3 log base 8 of x. Now this is now a log equation, so you want to isolate the log as much as you can before you try to undo it. And this does have a power on it, or it does have a coefficient on it. So you have a couple options. You could move it up to the power if you want, but it's probably just as easy to go ahead and divide through by that coefficient. There's multiple ways to do this, but I'm just going to think of it as a coefficient and divide through by it and get that log by itself. Now what we want to do is take 8 and raise it to this power and set that equal to its argument, which in this case is just an x. Now 8 to the 2/3, you probably don't want to leave your answer like that because that does reduce. So just a little reminder here. What do fractional powers represent? They're equivalent to radicals. And if this has a 3 in the denominator, that means we're really talking about a cube root. And we're talking about the cube root of 8. What about that 2 on top? Well, that's the power that this is being raised to. So the reason why 8 to the 2/3 reduces is because 8 is a perfect cube. So the cube root of 8 just becomes a 2, and then when we square that, that becomes 4. So your simplified answer would just be x equals to 4. And we did have some logs in this problem, so let's just double check our domain. If I were to plug in 4 for this x, we would be taking the log of a positive number, which is what we want. So this is valid, and we get x equals to 4. So that one's a little bit tricky. Let's take a look at the next example here. This one has a different look to it as well. It's got some e to the x's in it, but it also has some sort of polynomials involved as well, x squareds and x cubes. So when you look at this, and it may be hard to see the first time you do these problems, but the more experience you get with these kinds of problems, the easier it is to tell what you need to do. And the trick to this one, if you want to call it a trick, is to notice that this term and this term share stuff in common that you could factor out. So what's the GCF that I could factor out? Well, they both have an x squared, and they both have an e to the x. So I'm going to be left over with just a 3 from this first term plus an x from this second term. And now we have 3 things being multiplied together set equal to 0. So either the x squared has to be 0, or the e to the x has to be 0, or the 3 plus x has to equal to 0. So we're going to get 3 potential solutions. This one's easy, just -3. This one over here, when does x squared equal to 0? Well, that's easy, when x is 0. And then how about this one? When does e to the x equal to 0? Think about the graph of e to the x. It's exponential growth, and it has this horizontal asymptote at y equals to 0. When does this graph hit 0? Never, because it's an asymptote. It just grows asymptotically closer to it. So this is impossible. So there's not going to be any solutions from that part of the equation. So the only solutions I have are 0 and -3. And there weren't any logs in this problem, so I don't have to worry about any domain issues. So we don't really need to check. Okay, the next 2 examples are similar to each other in terms of the strategy that we're going to use, but they look very different from all the ones that we've done so far. E to the x equals x cubed plus 1. This one actually does look a little bit similar to the last one we did, but there's a huge difference. On the last one we did, we were able to factor some stuff out. And on this one, even if you move all your terms over to one side, nothing's going to factor out. What you were trying to do here is take an exponential function and figure out where it's going to equal a cubic polynomial. It's kind of like we're mixing up our different functions. We usually only know how to solve exponentials if it's just an exponential set equal to a constant, not necessarily an exponential set equal to a polynomial. So we're trying to mix things up here, which means that because it has an e to the x and an x cubed, and it doesn't factor, then chances are we're not going to be able to solve it. So we're probably going to have to break out the calculator. So if all else fails, you might have to resort to doing it graphically and getting an approximate value for the solution. So how are we going to do this? You have a couple options. I'll show you one way on this example and one way on the next one. Your 2 options would be either to set all of this equal to 0 and then find the zeros of that equation, or you can find intersections and graph this in y1, graph the right side in y2, and see where they intersect. So let's just do this one with zeros. I'm going to go ahead and subtract that x cubed to the left and subtract that 1 to the left and get a 0. So in my y1, what I'm going to type in is this e to the x minus x cubed minus 1 curve. So I'm going to type in that whole left side. And what we're going to be looking for here are looking for the zeros. We're not doing intersection points here, we're looking for zeros. So let's go to the calculator, go to y equals, and we're going to type in e to the x minus x cubed minus 1. I'm just going to start with the standard window, and remember we're looking for zeros here. So I see potentially a couple zeros here and maybe some over here as well. We might need to zoom in on our graph a little bit to be able to see this. Since I'm just looking for zeros, I just want to be looking in this sort of smaller window here. So let's change our window dimensions. Let's just go -5 to 5 for the x's, and maybe -3, whoops, -3 to 3 for the y. Since we're looking for y equal to 0, we don't need to be looking too high or too low. Okay, so we're going to go ahead and try and find these zeros. So let's go ahead and do our calc command, option number 2. And you're just going to move your cursor a little bit to the left of that leftmost 0. Then a little bit to the right, just a little bit below the 0, and then back up to the guess. Whoops, shoot, I messed that up, sorry about that. Let's try it again. Alright, third time's a charm, right? Let's try it again. Left bound. Right bound, guess. So -0.825 would be 1. So one solution is at approximately -8.825. Alright, let's try to find our other ones here. So we're going to do second calc, option 2. And I'm going to go just a little bit to the left of this 0, hit enter, a little bit to the right, hit enter, and a guess. That's really, really small. This notation right here, this is scientific notation, so this means 1.5 times 10 to the -14. So that would be 0.00000 and so on, 14 or 13 zeros and then the 1.5. So that's super tiny, and to me that's obviously close enough to 0 that we can just approximate that 0 to be 0. So I'm going to say my next solution is 0, and then we have a couple more to find here as well. So we're going to do second calc, option 2, go a little bit to the left, hit enter, a little bit to the right, hit enter, back up for the guess, and that is 1.545 for x. Okay, and then the last one, so second calc, option 2, and now we're going to need to go all the way to the right. You won't see that cursor for a little ways, and then eventually it should pop back up as we get closer. There it is. So it's very jumping quite steeply. So here I want a left bound, and right now I'm a little bit to the right of my 0. So I do want to back up once, but you won't see the cursor. That's okay. Hit enter. Hit the cursor to the right once so that you see it. Now we're a little bit above that 0 and to the right, so hit enter. And I'm just going to make that my guess as well. So we get 4.567 for the fourth 0. And there are my 4 different solutions. Okay? Now the next example is very similar to that. Again, we're trying to mix up these logarithmic functions, this ln, with a polynomial and trying to see where they equal each other. And typically when you're trying to compare two majorly different types of functions, like an ln versus a polynomial, it's very hard to compare the two. So what we're going to do is break up the calculator again, and this time I'm going to do it in a slightly different way. I'm going to let y1 be the left side of my equation, and I'm going to let y2 be the right side of my equation, and I'm going to graph these, and what I'm going to look for are the intersection points. So let's go to our calculator, and I'm going to go to my y equals, clear this out, and I'm going to type in ln of x in y1, and I'm going to type in x minus 4 in y2. Let's go back. Well, actually, I think our window might be okay. Let's just try the same window that we used before, and hopefully we'll get lucky and it'll be fine. So hit graph. There's that ln shape that we expect to see, and then there's our line, and I don't see my intersection points. They're outside my window, so we are going to need to zoom out here. So let's just go back to that standard window. There's that ln, and there's the line, the x minus 4. Now you have to remember that there's obviously an intersection point over here, but this ln graph does shoot downwards, so there is an intersection point over here somewhere as well. So let's go ahead and find the one that's up here first, the one that's more obvious. So we're going to do second calc. This time we're doing an intersect, so number 5. And I'm going to move my cursor along that ln graph until it gets close to that intersection point on the right. Hit enter. Second curve looks pretty good. Hit enter. Guess. Hit enter. So 5.749, comma 1.749 as well. So let me draw this picture to refer to. I should have drawn a picture on the last example, but I forgot. So you can revise your notes to show that graph. But this point is that 5.749 that we just found, comma 1.749. And then there's one over here as well that we're going to need to find. So let's go back to our calculator and see if we can locate that other intersection point, even though it's hard to see it on my graph because it's that ln gets so close to that y-axis that it almost looks like it just disappears. So let's go to second calc, number 5, and I'm going to go back down on my ln. Whoops. And you can't even see the cursor there. So there's the last place I'm going to see that cursor. If I move it to the left once more, it jumps off the curve. I might want to not use that point because you'll see that there's no y value there, and sometimes you can get an error on these. So I'm going to jump back to the right so I can physically see my cursor and hit enter for my first curve there. And then for my second curve, it's looking good right where it is flashing, so hit enter and hit enter for the guess. And there's my second point. So 0.01866, comma negative 3.981. So this was 0.01866, comma negative 3.98, something like that. And when you're writing your answers, remember this was really just solving for x, so you really only need to give these x values. Both of them are positive, so they're going to make ln of this x value defined. So both of them are valid solutions. Okay? Now the last thing that we're going to talk about is how to solve logarithmic and exponential inequalities. And what we're going to do is we're going to take the logarithm or the exponential of both sides, whichever is appropriate. So when we're solving these logarithmic and exponential inequalities, what we're going to want to be doing, for example, in this first problem, is to undo the logarithm. And what's going to undo a logarithm? It's going to be an exponential function. And on this example over here, what's going to undo that exponential with a base of e? It's going to be a logarithm with a base of e. So when we apply these inverse functions to our inequalities, we have to consider whether or not they are increasing functions or decreasing functions. And I hope that you remember from inequalities that whenever you multiply or divide by a negative, we always are supposed to flip the inequality around. Well, something similar is going to happen here. Whenever you apply a function that is decreasing, then you're going to have to flip the inequality around as well. So let me explain what I mean by that. If we take a look at this inequality here, we want to get just an x in the middle. So the only way to do that would be to undo this log base 1/2. And what function undoes a log base 1/2? Well, it would be the exponential with the base of 1/2. So what we're going to do is we're going to apply a 1/2 raised to various powers across this inequality. So what I mean by that is we're going to take a 1/2 to the left side, we're going to take a 1/2 to this middle expression, and we're going to take a 1/2 raised to the right side. So we're applying this 1/2 to the x function to all three parts of this triple inequality. Now think about the graph of 1/2 x for a moment. 1/2 raised to the x, that's an exponential growth or exponential decay. Because the base is a fraction, that makes it a decay graph. So it's going to start high and end low. So this is a decaying function, which means it is decreasing. And because it's decreasing, that's sort of equivalent to multiplying or dividing by a negative when you're talking about inequalities. Whenever you apply a decreasing function to an inequality, you have to flip it around. You have to flip those inequalities. So this less than or equal to is going to become a greater than or equal to, and this less than is going to become a greater than. Now we want to simplify. So what is 1/2 quantity cubed? Well, we know that that's 1/8. What is 1/2 quantity to the 5th? We know that that's 1/32. And how about in the middle here? This is one of those cancellation laws. This is like saying any exponential with a base of a raised to a log with a base of a, evaluated at some function x or some expression x, as long as these two bases match, the exponential and the log are going to cancel each other out, giving you just that x back again. So that's what happens on the middle here. This base 1/2 cancels with the log base 1/2, so we just get an x in the middle. But we now have these inequalities being flipped around. Now this would be our answer, but mathematically it doesn't look so great because in mathematics we always like to have the smaller number on the left and the larger number on the right, and 1/32 is smaller than 1/8. So I'm going to flip this around just to make it look a little bit nicer. Put the 1/32 on the left and the 1/8 on the right. I'm going to leave the x where it is, and because I'm flipping these two guys around, I need to flip the inequalities around too to maintain the correct inequalities. So right here, this greater than, which was between the x and the 1/32, is going to flip around to a less than, and this guy is going to flip around to a less than or equal to. So as an interval, this says all the x's that we want to use would be from 1/32 up to 1/8. I want a bracket around the 1/8 because of the equal bar, and I want a parentheses around the 1/32. So all of these x's in here would be solutions to my inequality. And all of these are positive x's, so they're not going to cause us any domain issues with our log. Okay? Let's try this again for this last example. So here we have e to the x squared greater than e to the 3x minus 2. So if we want to undo this exponential function, which has a base of e, then we'd want to use an ln on both sides. We'd want to apply the ln function to both sides. And I'm using ln because it has a base of e. So we're applying the ln to both the left and the right side. Now before I write in my inequality here, we have to consider whether or not it should flip or not. So think about what we were applying to both sides. We were applying the function ln of x. So you need to know what the graph of ln of x looks like. It's asymptotic to that y-axis, and it slowly rises up. So this graph increases. It's increasing. So here we do not have to flip because we're applying an increasing function to both sides. So this greater than symbol right here is going to stay a greater than symbol. So you only have to flip if your function decreases or decays, and you don't need to flip if your function increases. So here's our new inequality. The reason we chose those ln's is so that they would cancel out those base e's. So we're going to end up with just an x squared greater than a 3x minus 2. Now that's a quadratic inequality, so in order to solve it, I'm going to want to get a 0. So I'm going to subtract 3x and add 2 over to the left and get a 0 on the right. And there's a couple ways to do this, but I like to do it graphically. So I'm going to take a look at this quadratic function on the left-hand side, and I'm going to find out where it actually would hit 0. And luckily for us, this does factor. We get an x and an x, a 2 and a 1, and both of these are minus. So I'm going to get zeros at 2 and 1, and that means I have x-intercepts on my graph at 1 and 2. So if we draw our graph, we have a dot at 1 and a dot at 2. And this should be the graph of a parabola, right? Because it's an x squared, and it's a parabola that should point up because it's a coefficient of 1 in front of that x squared. It's positive. So this needs to be the graph of a parabola that points up. And I'm just doing a very general sketch. I'm not bothering to find the vertex. Really, the only points that are important to me are those intercepts. Because now what I want to do is find out where is this quadratic, where is this parabola greater than 0. Here is when it equals to 0, right at these two dots. So where is it greater than 0? Where does it lie above that? Well, that would be for all of these points on the parabola and all of these. But we just want to know what those x's are. So all of these points correspond to all of these x's, and all of these points correspond to these x's. So what interval would this be? Minus infinity up to 1, using a parentheses because we want strictly greater than. And then this interval would be start at 2 and go to infinity, and we want the union of both. And this was an exponential inequality, so we don't have to worry about any domain issues. So our final answer is minus infinity up to 1, union 2 to infinity. Alright, that concludes our video lecture on solving exponential and logarithmic functions. Good luck!